Now we move to the second speaker of the event, this part of the event, which I'm very excited because I have personal memory with that. Abiola, can you share the slide of Professor while I'm introducing him? Abiola?
Just a
Abiola, are you
minute.
there?
Can everyone see my screen now?
There.
Yes, okay. So Professor Bart Ermentrout is a famous mathematician and has worked in computational biology, but I know him personally from his software XPPAUT. My background during bachelor and master was in pure mathematics and computational algebraic geometry, so I didn't have any experience with mathematical biology when I wanted to start my PhD. Then I asked my PhD supervisor for several references, and one of the books that she introduced was a book titled Mathematical Modeling in Systems Biology and Introduction, written by Brian Ingalls. This book had an appendix for XPPAUT, if I remember, Appendix C, and it was a free software, so it was a good choice for me that time. I installed it and I solved all of the exercises of that book with this software. So I have personal memories with this software, and I'm very excited that now we have the opportunity of hearing from the developer of this software. He's going to talk about XPPAUT, a short historical perspective. Professor, please go ahead. Thank you.
Well, thanks for inviting me. It's funny, you were a pure mathematician. You were trained as a pure mathematician. Actually, my undergrad, and I got a master's degree and undergrad degree, I did number theory before I made the switch, because my feeling was that all the easy problems in number theory were solved 2,000 years ago. And I figured there was plenty of easy things to do in math biology. And it worked out. Anyway, so you asked me to kind of give a short historical perspective, and I'm going to conclude after this with a request, but I'll start out with that request too. I really would like to port this to a better GUI, and if anybody wants to be involved in that and would be willing to help me, I have some ideas, and just let me know. I'll put my email on at the end. Okay, so I think you can go to the next the next slide. Okay, so XPP actually started in 1988 in some sense, and I'll explain why. There was a course that was developed by Jim Bauer and Christoph Koch. They're sitting down there on the front there. And this course was a computational neuroscience. And John Rinzel, who was my postdoc advisor back in 79 to 82, he was invited to give a lecture on neural dynamics, and he wanted to have some sort of demonstration, computational demonstration that the students could use. So I basically, so we can go to the next slide. So we decided to work on the Morris-Lacar model, and during a visit to Oxford University, I developed a plotting program on my trusty compact portable 3. So this would have been probably, it was 87, I guess, 1987. And so I was able to plot things. And so you want to go to the next slide. So I basically wrote some runga of code to solve the Morris-Lacar equations. The null-clines in this case, for those of you who don't know what null-clines are, don't worry about it, but it's something that everybody that works in planar dynamical systems will use all the time. They can be explicitly computed, so you could draw those. And the interface allowed students to change parameters and the plotting view, time, voltage versus time, or voltage versus recovery variable. I used the plot routines I had to make this dedicated program that ran on DOS, I think, probably, because that's the only computers we had back then. All right, next slide. So What I really wanted to do, though, was to make general purpose software. And so the first software I developed was something I called Phase Plane, PHSPLAN. Graphics and numerics is all pretty easy, but I wanted a general purpose piece of software, so it had to be able to read the right-hand side. So I needed to be able to say convert minus x plus b times cosine y plus f of t into something that could be used by a machine. Now, again, a little history. Back in the early 80s, my first computer was an Atari 800. And the best programming environment for that was a language called Forth. And it's a stack-oriented language with an inner and outer compiler. All right. And its big advantage was it was RPN, reverse Polish notation, like the old HP calculators. So if you switch to the next slide. So the stack structure of Forth inspired my compiler. And in fact, this is a software I wrote for the Atari 800. You can look it up. I think you can still download it and play it on Atari emulators. It's the best paint program ever written for the Atari. So there it is, Rembrandt. In any case, you can probably dig it up somewhere. I know there's lots of Atari archives. So I used the structure of Forth to inspire my compiler. So if you want to go to the next slide, no user wants to write ODEs in RPN. So if you wanted to write minus x plus b cosine y plus f of t in RPN, what you would have to do is write x negate b y cosine times plus t f plus. And nobody wants to do that. So I had to learn all about operator precedence in order to make a mini compiler that could convert algebraic expressions into RPN. Now, I never programmed, I never took a computer course. So I basically just made all this crap up. I kind of took it logically. Okay. So this is just some little snippets of code. This is my algebraic to RPN converter. And next to it is sort of a list of all the symbols that I want, the tokens that people can use. And I think the first, second, third, fourth column is the precedence. I don't know how many of you guys ever, in the US, they teach us precedence by using the phrase PEMDAS, parentheses, exponentiation, minus and plus, I think, or no, multiplication, division, and addition and subtraction, or something like that to give precedence. But computer doesn't know that. So this is sort of like a little blurb of my early beginnings in trying to write a compiler. So from scratch. So if you want to go to the next slide. So basically what I did was, long before Java and anything else, I wrote a way to convert your right-hand sides into a sequence of byte code, okay? So each equation is converted into a series of 64-bit integers that encode functions, variables, floats that could be rapidly evaluated and pushed up and down on the stack. I needed to deal with things like if statements and sum statements and functions calling other functions and delays. So it ends up being very, very recursive. And not only is it really recursive, but it's really bad style. If anybody's ever written any modern programming languages, GoTo doesn't exist, but GoTo is still there. If God hadn't intended us to use GoTo statements, then C would not contain a GoTo statement. In any case, there is just a bunch of bits about how this fast compiler, or once it's compiled, this fast inner loop for interpreting that and producing output. If anybody's interested, I mean, this is a supposed to be a bunch of algorithms. And so these are some algorithms that I sort of invented to do things that are not things that mathematicians usually think about, like writing code for plotting. That's really easy. Or writing code for solving differential equations. I mean, I can't imagine anybody here hasn't written an Euler algorithm at some point in their life. But this was completely foreign to me, and didn't know how to approach it, except kind of I made it up, as I said. So next slide, please. So the first public version was released commercially through Brooks Cole in 1990. And there it is. It's phase plane. It's a DOS program. It was limited to 20 differential equations, I think 20 parameters, 20 functions, and it worked only on MS-DOS. And it was sort of set up as a competitor maybe to another program called Phaser that was also an ODE solver that was also limited to a certain number of ODEs. But I think that was even more limited than phase plane. But this version from 1990 was able to still find equilibrium points, integrate differential equations, and do some null Kleins. I actually probably should have put a few slides about how I used to do null Kleins and how I changed my null Klein algorithm over the years. But if anybody's interested, I can talk about it a little bit afterwards. All right, let's go to the next slide. This is going to be a pretty short talk, I think. So in early 1990s, there was a conference at Berkeley in math biology or something in MISRI, Mathematical Sciences Research Institute at Berkeley. So I was out there for like 2 weeks for this workshop. And during the evenings, I had recently acquired a Sun workstation. And so during the evenings, I would look out the window in Berkeley, and I converted the MS-DOS version over to Unix using the X11 window environment. At the time, there were many GUI toolkits, but most of them were mutually incompatible and also didn't work on all computers. So that's why XPP has such a crappy interface, because I wrote it from scratch from pure X11 so as to be compatible with the largest number of machines. I didn't want to use any GUI toolkits that wouldn't be available on this machine, but available on that machine. And around the same time, I think in the mid-90s, hold on, I'll be right back. I want to get something. Okay, this is the first laptop that was ever made. Okay, this is a T1200, and I downloaded on my Sun workstation 35 floppy disks and installed Linux on this laptop. I also had to write a graphics driver because at the time the graphics didn't work, but that worked. I got that to work also. So in the mid-90s, I migrated to Linux. I'm not actually sure of the public availability at that point. Mostly, I think I did it for my own use. I was going back over the Internet Archive or whatever, the web, what's it called? There's an archive of old web pages, and I found late 90s versions of XPP available. So I would say sometime in the late 90s was the first public availability of the X version. I know it was more like the mid 90s, because I remember right before Gordon conference. Can you go to the next slide? Sometime in the late 90s, I used the Fortran to C library, and managed to, Auto 86 was a bifurcation package written by Sabius Dodell, but it was written in Fortran, and XPP was written in C. So there was something called the F to C library, which would convert Fortran to very bad or very ornate C. But I did that. I completely converted all of Auto 86 to C, and then I was able to, include that into XPP. And at the time, this ran on Unix and Linux computers, and eventually that was made available to the general public. At the time, GCC, which is the standard GNU compiler, was available on Mac, and by the late 1990s and early 2000, versions were available for Mac OS and also older PowerPC. Mac ran an internal X11 server, which was eventually replaced by something called Xquartz. And for the Windows side, there was a Unix-like suite with GCC called Cygwin, and I used Cygwin to compile a version that ran under Windows, and then there was something called Xming, which was an X11 server for Windows, and the combined thing there allowed you to run it under Windows. So from about the late 90s until now, it's run on the all Linux platforms, Windows platforms, and Mac. So if you want to go to the next slide. So the first public release of XPP was a version 4 and version 5. And as I said, by 2000, public versions for HP Unix, Spark, Windows, Linux, and 2002 Mac OS was added. And then I know it's by 2002 because in 2002 is when I wrote the XPP book, simulating and analyzing and animating dynamical systems. There were lots of things I did in the meantime, like making a little animation language that you could run. I always wanted to make cartoons when I was a kid, and in fact, there's one of my cartoons that I made when I was 17. You can find on YouTube, so I was always interested in animation, and this was a nice way to animate differential equations. So I made a little animation language, which would take your outputs of your ODEs to make animated simulations. So can you go to the next slide? So 2011 and 2012, I was contacted by Ashutosh Mohan, who oh, okay, I'll do that. So Ashutosh Mohan did all the programming for this on the iPad. Here's a screenshot from the iPad version. It only lasted for a few years. I still have one iPad, an iPad mini, that I've never updated so that I can continue to run the XPP app on that, because once they went past some iOS, they kept changing the requirements, and you have to pay money to make it available in the Apple Store and so on and so forth. A real pain. So in any case, it only was there for a while. But it had a great interface, but it didn't have auto. But it was pretty quick too, and it just, it had a really nice interface at the time. And it's something that I would like to do on a more, on a computer version. So next slide, please. In 2016, Michael Baumgartner took advantage of silent mode in XPP to create a web-based interface, and there's a link for it. You can actually try it. It's still there. And actually, this is a screenshot I took 2 days ago from it. It's kind of clunky and it doesn't always work, but it sort of works. But again, it doesn't have auto or anything. But it can import. You can write your own ODE write your own differential equations, or you can actually read ODE files from it. But it does work. So I guess next slide. In 2015 to 2020, I upgraded the auto version using Auto 2000 and eliminated all the Fortran to C overhead. And that includes HomeCont for homoclinic continuation. I added a lot more options and customizations, more functions, et cetera, et cetera. And I think, let's see, is this the last slide? So XPP Impact, as of 2024, it's been used in over 2,500 academic papers. It's the 5th most used platform in ModelDB, which is a database. Translation of ODEs into CellML and vice versa. There's lots and lots of YouTube tutorials and published tutorials. And I always like to say it kind of brought bifurcation to the masses because I think, and I still think that my auto interface is the easiest one of any of them out there. And I've managed to teach lots of people that have no math background how to at least draw serviceable bifurcation diagrams. So let's go to the last slide, I think. Oh, future. Yeah. So X11 is not really a tenable graphical interface. It's over 30 years old. I love to talk to anyone who would like to work with me in porting it to a different GUI. I'm thinking Qt might be the best way as it's cross-platform and it's in C++. I've already managed to compile a linkable library of all of XPPAUT's functionality. I haven't done much testing of it, but that should make it easy to call anything you want. And so basically what I need to do is de-exit. I'm not getting any younger, and I've occasionally looked into funding organizations, but there's nothing that seems available for this. So if anybody's interested in helping, there's my email, and I'll stop here. It's 300,000 lines of C code. I can tell you that. Probably not really well organized either, because X is interleaved in lots of places, but we managed to unbundle it from X pretty easily for the iPad version. So I don't think it'll be ridiculously hard.
So we've got still a few minutes to the next speaker. So still we have time for questions.
Somebody asked if I was ever, did I ever commercialize it? No, in fact, but let me tell you a funny story, okay? So I don't know, maybe 20 years ago, on my web page, I had suggested if you want to keep XPP going, you know, you send a little money or something. So a couple people sent me like checks for $5 or something. But one day, about 2 years ago, about 20 years ago, probably, maybe even longer than that, I got a check in the mail for $4,000 from a guy in who worked at DuPont, I think, DuPont in Delaware. So it was he was an industry guy, and he said that my software was the only one that they found that could solve these stiff chemical differential equations that they had. So that was sort of the closest I ever got to commercializing it. But I've never commercialized it. It's always been free for the masses. Yes.
Okay, great. Please go on. Ask your question, please.
I take it you're from Thailand.
Sorry, I just misclicked. I have no question.
Huh?
Oh, okay, that's fine.
Oh, no question? Okay.
Sorry for the problem from my side, the internet connection. I just moved from home, running to the office. And I'm sorry to the first two speakers as well. I heard until near to the end of Professor Ermentrout presentation. I'm sure many of our students will contact you for the GUI offer that you gave. We have software developers in the meeting, and there will be a lot of other students that will watch the recorded video later after the summer vacations. Did anyone have any question? No? I can maybe I can ask one quick question from Professor Ermentrout on behalf of the students, especially the early students in bachelor, that may ask some advice for starting in mathematical biology. As you said, you were in number theory, or myself, I was in the pure mathematics, and then we suddenly switched. But what they should do if they want to start now, do you have any advice for them?
You know, I joined math biology. I mean, I got into math biology because I was when I went to college, I was actually a pre-med chemistry major. And so I was sort of interested in medicine, but I took a course in advanced inorganic chemistry, and it was all about group theory and molecular orbitals and things like that. So I switched to math and fell in love with number theory and things like that. But then towards the end of my time as a grad student or undergrad, I thought, well, you know, maybe I should think about med school again. And so I started reading about math bio, and I found it really interesting that you could, you know, use, at the time I was reading things like by Renee Tom and things like that. And I thought, wow, this is really cool. Hardcore mathematics you can use to solve biology. So that's how I ended up in the field. I would say that it's not that if you're looking to get in the field early on, the tools I use are dynamical systems and differential equations. And I was self-taught in that. I never took in college, I didn't take any courses in ODEs or anything because I was a pure mathematician. But so I would recommend that. And I think one thing that I hate to admit it, I'm not going to learn it because I'm too old, is ML is going to be a big thing in biology and every other field. So you're going to have to learn that, unfortunately.
Yes, so I remember my PhD supervisor also, because at the beginning I was saying I like pure mathematics because of difficult problems and things. And then she said that there are a lot of things in applications such as biology that you need advanced tools from mathematics, and you will find difficult problems there as well. So yes. Yeah, and differential equations are really important, and I started with them too. The book that I said, with the help of your software, I solved the exercises, and yeah, that was the initial step I had myself.
And I think the most important thing is to find a biological collaboration that you can work with, because it kind of keeps you honest. And it's also a lot of fun. I mean, I just started well, I won't say just started, but it's been a few years. But I just started a project a few years ago that's super fun. It's all about the math of, I mean, we're interested in the rhythmicity of the colon. So it's kind of gross, but it's real important.
Yes, it has its medical purposes.
And unlike rhythms in the brain, we know exactly what the rhythms in the colon are good for. So anyway, but I that's something I would suggest. I would suggest maybe if you're an undergrad, doing research is a great idea. Just undergrad research, even if it's nothing that ever gets published or anything, it's still a great experience. Because a lot of people coming to grad school not really knowing what mathematical research or any other kind of research is. So I would suggest, you know, doing some sort of undergrad projects or something like that. Unfortunately, you got to do a lot of reading, and you got to read biology papers. So it's good to know. That was an upside of being a pre-med, is I took all the organic chemistry and biochemistry and cell biology. So I knew a lot of biology already, so that helped a lot. I know, like I have a PhD student now that's pure math, and he left pure math halfway through his graduate work, and he basically really struggles with the biology because he's never had it as an undergrad or anything else. So I think that's really helpful.
Okay, thank you, Professor Ermentrout, for the advice and the suggestions.